Assalamualaikum and hello everyone. We are from AS120 Group 4 and currently in our 4th semester. We are going to presenting about drug testing with chromatography. I like to introduce our group members. Starting from the left is Aina Raihana, Amira Nashira, Nurul Huda, and the last one is myself, Siti Zalina. Now, I will introduce two important concepts, which is drug testing and chromatography. So, what is a drug test? It is a process that uses a biological sample, such as urine, to detect the presence or absence of legal or illegal drugs in the body. These tests are commonly used in healthcare, workplace, and law enforcement. Next, chromatography. Chromatography is an important biophysical technique that enables the separation, identification, and purification of the component of a mixture for qualitative and quantitative analysis, which means it helps us find out what is in a sample and how much of is in there. These concepts are crucial for understanding how drug tests work and how accurate results are obtained. Now let's understand why chromatography is very important. Chromatography is a highly sensitive technique that can detect even very tiny amount of drugs and their metabolites, even when they're present in very low concentrations. This method is also used in the pharmaceutical field. It helps verify the presence of the correct active ingredients known as APIs in drugs. Plus, it can detect any impurities or degradation products, ensuring the medicine is safe and effective.
Chromatography is a physical method used to separate the component of a mixture. The key idea is that the components are distributed between two different phases, which is the stationary phase and the mobile phase. The stationary phase can be either a solid or a liquid that is supported on a solid. It stays fixed in place, and on the other hand, the mobile phase is a liquid or a gas that moves through the stationary phase. Next is principle of chromatography. The principle behind chromatography lies in the different ways substance interact with these two phases. Some components of the mixture will stick more to the stationary phase, while others prefer to move with the mobile phase. Because of these different interactions, the components travel at the different speed, and this is what causes them to separate over time. The theory of chromatography can be divided into two main parts. The first one is the plate theory, also known as the equilibrium theory, and the second one is the rate theory. Let me start with the first one, which is the plate theory. This theory was developed by Martin and Stinch in 1951. It explains how separate occurs using the idea of imaginary layers inside the column. These layers are called theoretical plates. Each theoretical plate represents a point where the solid reaches equilibrium between the mobile phase and the stationary phase. As the solid moves through the column, it keeps balancing between these two phases at every step. The more theoretical plates a system has, the more efficient it is at separating the different components in a mixture. To understand the efficiency of a chromatographic column based on the plate theory, we use two important calculations. The first one is the number of theoretical plates represented by N. It tells us how many imaginary equilibrium steps or plates exist in the column. The formula to calculate N is N equals the square of the retention separation time divided by the standard deviation of the peak, or alternatively, n equal 16 times the square of the retention time divided by the width of the chromatographic peak. And the second one is the Higg equivalent to a theoretical plate, written as H or HETP. This tells us how long each plate would be if the column were physically divided, and the formula is H equal L divided by N, where L is the length of the column and N is the number of theoretical plates. A smaller H value indicated better separation efficiency because it means more plates can fit into the same column length. Next, let's move on the second theory, which is the rate theory, also known as the kinetic theory. This theory was proposed by Mdm Diana in 1956, and it explains how band broadening occurs in chromatography due to the time-dependent factor. In simpler terms, it looks at how the solute spread out as it moves through the column and why that happens. Rate theory focuses on the speed of the solute and how it interacts with the column during the separation process. These are three main causes of band broadening in this theory. First, we have eddy diffusion. It also called the A terms. This happens because solute particles take different paths through the packed particle in the column. Some paths are shorter while others are longer, which lead to the uneven travel times and cause the band to spread. Second is longitudinal diffusion, known as the B terms. Here, the solute naturally spread from areas of high concentration to areas of low concentration as it moves forward. This effect becomes more noticeable at low flow rates. Third is mass transfer, or the C terms. This refers to the time it takes for solute molecule to move between the mobile phase and the stationary phase. If the movement is not fast enough, the solute doesn't fully equilibrate, especially at high flow rates, which result in a border peak. Now, we will move to Mdm Diana equations. These equations show the relationship between column efficiency H and flow rate, which is U. H equal to A plus B divided to U plus C multiplied by U, where H is Higg equivalent to a theoretical plate and U is a flow rate of the mobile phase, and A, B, and C is a constant for eddy diffusion, longitudinal diffusion, and mass transfer.
Let's talk about the principle of thin layer chromatography, or TLC, toward drug testing. TLC is a separation technique that uses a thin layer of adsorbent like silica gel or alumina and coated on plate. This technique used to separate compound in mixture based on the different affinities for two phases, which is a stationary phase TLC plate with a silica gel and a mobile phase, which is a liquid solvent. So, how it works? A sample on a plate coated with a solid and letting a liquid to move up the plate. As a liquid raises up, the sample's component move at a different speed on how strongly stick to the plate or dissolve the liquid. This will causes the component to separate into distinct spots. Non-polar drugs are weakly adhere to silica. They move faster with mobile phase, while polar drugs is a strongly bound to stationary phase, and they will move slower with a mobile phase. Next, there are 6 techniques to testing the drugs by TLC. First and foremost is sample preparation. By extract the drugs from the sample like urine, blood or hair using a solvent like methanol or ethanol. Second step is stationary phase preparation by using a glass TLC plate coated with a thin silica gel layer. Next is a sample application. By draw a line on the plate and apply sample as a small spot using a capillary tube. Continue with development, which we can place the plate in a chamber with solvent. Solvent will raise up by capillary action and carrying sample. After that, we can do detection by using a UV light, hydrant spray, sulfuric acid or even iodine vapor. Lastly, we do an analysis with RF value calculation, densitometry and compare with standard. After all the technique is done, we can calculate the RF value to identify the substance. The RF value is calculated using this formula. RF equals the distance moved by the substance and divided by the distance moved by the solvent. In this example, the solvent traveled 12 cm from the baseline. The red substance spot moved 5 cm. So, RF equal to 5 divided by 12 and you can get 0.42. This value can be compared to reference standard to identify the substance. Keep in mind, the solvent used here is water and the substance is shown as a red spot. After developing the TLC plate, the next step is to visualize the spot where the substance separates. This helps us to identify the component present. There are two main methods of visualization. First, by using the UV light. These include tools like a camera to capture the TLC result, a dark room or UV viewing box to safely observe the fluorescent spot, a UV cabinet for controlled exposure, and a handheld UV lamp for flexible, close-up examination of spot that fluoresce under UV light. Second, the standing visualization method. This method helps when the spot not visible under UV. It involves a TLC spray bottle to apply chemical reagent, a spraying cabinet for safety during the spraying, and a spray box to contain fumes and prevent a contamination.
To begin, based on the diagram in the slide, you can see the basic setup of thin layer chromatography. At the bottom, the developing chamber contains the solvent, also called the mobile phase. A TLC plate is placed upright inside the chamber. It's coated with silica gel, which acts as stationary phase. Near the bottom of the plate, there's a sample spot applied carefully using a capillary tube. The solvent level is kept below the sample spot, as shown in the diagram, to avoid direct mixing. As the solvent rises through the plate by capillary action, it carries the compounds upward. These compounds move at different rates depending on their polarity and eventually form separate spots at different heights. The setup allows us to separate and analyze the components in a mixture effectively. Now, let's proceed to the first TLC result, where marijuana and hemp extract are analyzed side by side. On the TLC plate, both samples are spot onto the silica gel surface, one lane for marijuana and one another for hemp. The plate is then placed in a developing chamber with a selected solvent. As the solvent moves upward, it carries the compounds along. After development, the plate shows distinct spots for each sample. From the diagram, we can observe that the marijuana lane shows a spot matching THC while the hemp lane matches CBD. This separation happens because CBD and THC have slightly different polarities, so they travel different distance on the plate. This TLC setup helps to visually distinguish the chemical content of each extract, clearly showing that hemp contains CBD and marijuana contains THC. It's a simple and effective method for comparing two similar plant extracts using just one plate. Aside from that, this TLC plate gives us another useful comparison: cannabis versus tramadol. Cannabis contains natural compounds like cannabinoids,
while tramadol is a synthetic opioid with a completely different chemical structure. As shown on the plate, the spots from these two substances appear at clearly different positions, showing how well TLC can spread them. This kind of result is really important in areas like forensic and toxicology, especially when identifying a known substance in biological samples or seized materials. Even though TLC doesn't give exact concentrations, it's still a quick and affordable screening tool often used before more advanced tests like GC-MS.
In conclusion, chromatography is a powerful and reliable technique widely used in drug testing due to its high sensitivity, accuracy, and ability to separate complex mixture. The techniques such as gas chromatography, liquid chromatography, and thin layer chromatography play a crucial role in contemporary drugs testing practice. Their versatility allows for the analysis of a broad range of substances, making them suitable for diverse applications such as forensic investigation and pharmaceutical quality control.